Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home on your commute or winding down for the evening, I'm really glad you're here. Picture this. It's December 15th, 2019. 3:47 in the morning, Hawaii time. Most of the world is fast asleep, but high atop Mauna Loa volcano, something extraordinary is about to happen. The Atlas telescope, that's the Asteroid Terrestrial Impact Last Alert System, is doing what it does every clear night, scanning the heavens for anything that might threaten Earth. But tonight, it's going to capture something that will turn everything we think we know about our cosmic neighborhood completely upside down. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Now, here's what makes this moment so incredible. In 400 years of serious astronomical observation, from Galileo's first telescope to our most sophisticated space-based instruments, we've catalogued millions of objects. Asteroids, comets, planets, moons. We think we understand how things move in space. Newton's laws are rock solid. Objects follow predictable paths based on gravity and momentum. It's elegant, it's mathematical, and it works every single time, until this night. The computer systems at Atlas flag an anomaly. Something is moving through our solar system at 67,000 miles per hour. Now that might not sound too unusual. Space is full of fast-moving objects. But here's where it gets interesting. This thing is coming from deep interstellar space, from beyond the gravitational influence of our sun. It's what we call a hyperbolic trajectory, which is just a fancy way of saying it's passing through, not sticking around. Think about that for a second. This object has been traveling through the vast emptiness between stars for who knows how long. Hundreds of thousands of years, maybe millions. And now it's here, in our little corner of the galaxy, giving us a brief glimpse before disappearing forever into the cosmic void. But wait, there's something else. Something that makes the astronomers sit up and take notice in a way they haven't in decades. This visitor isn't just moving fast. As it approaches the sun, it starts to accelerate. Not in the way we'd expect from gravity alone, but with an additional push that shouldn't exist. You know what this reminds me of? Imagine you're driving down a perfectly straight, flat highway with your cruise control set. Suddenly your car starts speeding up on its own. No extra gas, no downhill slope, no explanation. That's essentially what's happening here, except instead of a car, it's a massive object hurtling through space. And instead of a mysterious acceleration of a few miles per hour, we're talking about forces that would require enormous amounts of energy to produce. The team assigns it a designation, 3I Atlas. The 3. And the I tell us it's the third confirmed interstellar visitor to our solar system. The first was Oumuamua, back in 2017, a strange, elongated object that also showed non-gravitational acceleration. The second was Comet Borisov in 2019, which behaved more like a traditional comet. But 3I Atlas? This one's different. This one is breaking the rules in ways that make even seasoned astronomers scratch their heads. Here's what's so wild about this discovery. We've been looking up at the night sky for thousands of years, right? Ancient civilizations tracked the movements of planets, predicted eclipses, built monuments aligned with celestial events. For most of human history, the heavens seemed eternal and unchanging. Sure, occasionally a comet would appear, but even those followed predictable patterns once we understood them. Then, in the span of just 2 years, we discover not one, not two, but 3 objects from interstellar space passing through our solar system. 3 messengers from distant stars, each one carrying information about conditions in other parts of the galaxy. What are the odds of that happening just as we develop technology sensitive enough to detect them? It makes you wonder, doesn't it? How many of these interstellar visitors passed through our solar system before we had the tools to spot them? How many cosmic postcards from alien worlds sailed right by while we were still learning to make fire, or building pyramids, or arguing about whether the Earth was round? But let's get back to 3i Atlas and what makes it so extraordinary. As observatories around the world turn their instruments toward this mysterious visitor, something becomes clear. This isn't behaving like any comet they've ever seen. Traditional comets are basically dirty snowballs, chunks of ice and rock that formed in the outer reaches of star systems. When they get close to a star, the ice begins to sublimate, creating those beautiful tails we see stretching across the sky. Here's the thing, though. 3i Atlas shows no signs of typical comet activity. No tail, no visible outgassing, no hydrogen signature that would indicate water ice vaporizing. It's like a ghost comet, producing the acceleration we'd expect from a comet without any of the visual evidence that usually comes with it. Now I know what you're thinking. Maybe it's made of different materials? Maybe it's a comet composed of substances that don't produce visible outgassing. Scientists considered that possibility. They ran calculations, built models, tested every known mechanism that could produce this kind of acceleration naturally. And here's where the story takes a turn that even the most imaginative science fiction writers would find hard to believe. There's one scientist, a respected Harvard astronomer named Avi Loeb, who's been following this mystery closely. 2 years earlier, when Oumuamua showed similar anomalous behavior, Loeb proposed something that sent shockwaves through the scientific community. He suggested, seriously in peer-reviewed papers, that these objects might not be natural at all. They might be artificial. They might be technology from another civilization. Most of his colleagues dismissed the idea. After all, extraordinary claims require extraordinary evidence, and there had to be natural explanations for what they were seeing. But now, with 3i Atlas displaying even more dramatic non-gravitational acceleration, 6 times stronger than what Oumuamua showed, Loeb's hypothesis doesn't seem quite so far-fetched. Picture this scenario. 1 million years ago, maybe more, an advanced civilization somewhere among the stars decides to explore the galaxy. Not with crude starships, that would take too long, require too many resources. Instead, they launch thousands, maybe millions of robotic probes. Each one is equipped with a gossamer-thin light sail, designed to catch the pressure of starlight and solar wind. These probes are built to last, constructed from materials we can barely imagine, engineered to survive the harsh environment of interstellar space for eons. Most of these probes pass through empty space, reporting back data about the void between stars. But occasionally one encounters a star system. It adjusts its trajectory, using its light sail to maneuver closer to the central star, gathering data about planets, moons, asteroids, everything that might tell its creators about the potential for life in this corner of the galaxy. Then, mission complete, it adjusts course again and continues on its endless journey, carrying its precious cargo of information to some distant rendezvous point where other probes wait. Or perhaps transmitting its findings across the vast distances to receivers we can't even conceive of. If this sounds like science fiction, remember that we're already planning similar missions ourselves. Projects like Breakthrough Starshot aim to send tiny probes to nearby star systems using exactly this kind of light sail technology. The physics works. The engineering challenges are enormous, but not impossible. A civilization just a few centuries more advanced than us could absolutely build something like what we're observing. But here's what really gets me about this whole scenario. If 3i Atlas is indeed an alien probe, it represents something profound and unsettling. This isn't the dramatic first contact that Hollywood has trained us to expect. No giant ships hovering over major cities, no attempts at communication, no interest in our planet or our species at all. Instead, it's more like finding an empty ship drifting past a remote island. You know others have sailed these waters, but they're long gone, and you're left with more questions than answers. Where did they come from? Where are they going? Are there more of them out there? And perhaps most troubling of all, why haven't they tried to make contact? The implications are staggering. If true, we're witnessing the casual exploration of our solar system by a technology so advanced that we barely register as significant. We're not important enough for a hello, not interesting enough for a closer look. We're just another star system to be catalogued and forgotten. Or maybe, and this is equally fascinating, the probe is so old that its creators are extinct. Maybe we're seeing the ghost of a dead civilization, their final automated emissary, still carrying out its programmed mission millions of years after the last member of their species drew breath. Their bodies are dust, their worlds are silent, but their technology continues its patient exploration of the galaxy. Either way, everything changes. The universe suddenly feels less empty, but also more lonely. We're not alone, but we're not significant either. We're witnesses to something incredible, but we're powerless to do anything about it, except watch and wonder. As 3I Atlas continues its journey away from the sun, picking up speed with each passing day, astronomers around the world work frantically to gather as much data as possible before it disappears forever into the darkness between stars. Every observation might be crucial. Every measurement might hold the key to understanding whether we've just witnessed the most important discovery in human history or the most spectacular case of mistaken identity. The race is on, and the stakes couldn't be higher. Because if Avi Loeb and others like him are right, if this mysterious visitor really is technology from another world, then December 15th, 2019 will be remembered as the day everything changed. The day we learned that we share the galaxy with others who have been quietly exploring the cosmos, while we were still figuring out how to leave our own planet. But we're getting ahead of ourselves. Before we can understand what 3I Atlas might mean for humanity, we need to go back to the beginning. We need to experience that December night when everything started, when a routine survey of the sky turned into one of the most extraordinary discoveries in the history of astronomy. So, let's step into the Atlas control room on Mauna Loa and witness the moment when our understanding of the universe began to shift in ways we never expected. Let me take you back to that December night on Mauna Loa. Picture Larry Deneau, the lead astronomer for the Atlas survey, sitting in front of a bank of computer monitors in a control room that looks more like mission control than what most people imagine when they think of an observatory. There's no romantic dome with a massive telescope pointed at the stars. This is all automated, all digital, all about processing enormous amounts of data at lightning speed. Larry's been doing this for years. Night after night, the Atlas telescopes scan the sky, taking hundreds of images, comparing them to previous observations, looking for anything that moves or changes brightness. Most nights, it's routine work. A few new asteroids, maybe a known comet brightening as it approaches the sun. Nothing that would make headlines. His coffee has gone cold hours ago, but he doesn't notice. The automated systems are flagging something unusual. And when you're responsible for humanity's early warning system against potentially dangerous asteroids, unusual demands your full attention. Here's what the computer is telling him. There's an object moving across the sky at a rate that doesn't make sense for anything gravitationally bound to our solar system. The trajectory calculations are spitting out numbers that suggest this thing came from interstellar space. And that means it's only the third confirmed visitor of its kind in human history. Now, think about what that means for a moment. In all of recorded history, going back thousands of years of astronomical observation, we'd never detected a single object from interstellar space. Not one. Then in 2017 we spot Oumuamua. 2 years later, Comet Borisov. And now, just months after that, here comes 3I Atlas. Either we've suddenly gotten incredibly lucky, or these interstellar visitors are more common than we ever imagined. Larry immediately knows this is big. Not just interesting to astronomers big, but change everything we thought we knew big. He starts making calls. Within minutes, observatories across the Pacific are swinging their instruments toward this mysterious visitor. The Subaru telescope in Japan, with its 8-meter mirror and cutting-edge instruments, captures the first detailed images. What they see is strange. Most objects in our solar system are either roughly spherical, like planets and large asteroids, or show the fuzzy, diffuse appearance of comets with their tails of gas and dust. 3i Atlas doesn't fit either category. It appears elongated, maybe 10 times longer than it is wide, tumbling end over end as it travels through space. The first thing that strikes everyone looking at the data is how faint it is. This object is small, probably no more than a few hundred meters across at its widest point. But here's the kicker. Despite its tiny size, it's producing an acceleration that would require enormous forces if generated by conventional means. Dr. Robert Verick, the astronomer who discovered Oumuamua 2 years earlier, is among the first to see the preliminary observations. The similarities are unmistakable. Both objects are elongated. Both show non-gravitational acceleration. Both are incredibly faint and difficult to observe. But 3i Atlas is accelerating 6 times more dramatically than Oumuamua ever did. You know what this reminds me of? Imagine you're a detective and you've just solved your first truly bizarre case. Something so weird you're not sure anyone will believe it. Then before you've even finished writing your report, another case lands on your desk with exactly the same impossible evidence. At some point you have to ask yourself, is this really coincidence, or is something bigger going on here? The race against time begins immediately. Unlike planets or asteroids that orbit the sun and can be observed for years or decades, interstellar visitors are just passing through. They give us a brief window, weeks or months at most, before disappearing forever into the cosmic void. Miss your chance, and that's it. The opportunity is gone for millions of years, maybe forever. Observatories around the world join the effort. The European Southern Observatory in Chile, the Keck telescopes in Hawaii, the Hubble Space Telescope, everyone who can get a clear view starts pointing their instruments at this mysterious visitor. But there's a problem. 3i Atlas is moving fast and getting fainter by the day as it speeds away from the sun. Here's where the story gets really interesting. As the observations start pouring in, patterns emerge that make absolutely no sense according to our understanding of how objects behave in space. Traditional comets follow a predictable script. As they approach the sun, frozen gases on their surface begin to sublimate, creating jets of material that not only form the beautiful tail we see, but also act like tiny rocket engines pushing the comet around. This process is well understood. We can predict exactly how much acceleration a comet should experience based on its size, composition, and distance from the sun. The math works perfectly for thousands of known comets. But 3i Atlas breaks every rule. The acceleration is there, undeniably present in the tracking data. But the visible signs of outgassing that should produce that acceleration, nowhere to be found. Spectroscopic analysis, which can detect even tiny amounts of water vapor, carbon dioxide, or other typical comet materials, comes up empty. It's like having a car that somehow accelerates without burning fuel. Dr. Marco Micheli from the European Space Agency leads the team analyzing 3i Atlas's trajectory. He's the same scientist who definitively proved that Oumuamua was experiencing non-gravitational acceleration, so he knows exactly what to look for. His preliminary calculations show something that makes him double-check his work multiple times. The acceleration of 3i Atlas is not only stronger than Oumuamua's, it's more consistent and sustained. Picture this. You're watching a magic trick where the magician makes a coin disappear. The first time, you're impressed, but figure there must be a simple explanation you're missing. The second time, with a different coin, you start to wonder if maybe this person really does know something you don't. That's essentially where the astronomical community finds itself by early 2020. The data keeps getting stranger. Light curve analysis, which measures how an object's brightness changes as it rotates, suggests that 3i Atlas is highly elongated, possibly cigar-shaped or pancake-flat. It's tumbling every 7.3 hours, and as it tumbles, we see different amounts of its surface area. causing its brightness to vary in a predictable pattern. But here's what's weird about that. Most natural objects in space are roughly spherical because gravity pulls equally in all directions. To get something as elongated as what we're seeing with 3i Atlas, you need special circumstances. Maybe it's a fragment broken off from a larger object, or maybe it formed under unusual conditions, or maybe it's not natural at all. The implications start sinking in among the scientific teams. Dr. Avi Loeb at Harvard, who had already stirred controversy by suggesting Oumuamua might be artificial, watches the 3i Atlas observations with growing fascination. 2 years ago, his colleagues dismissed his ideas about alien technology as premature speculation. But now, with a second interstellar object showing even more dramatic anomalies, his hypothesis doesn't seem quite so outlandish. Loeb starts running calculations. What would it take to produce the observed acceleration through artificial means? The answer is surprisingly simple: a light sail. An extremely thin sheet of reflective material, perhaps just micrometers thick, could catch the pressure of sunlight and solar wind to produce exactly the acceleration they're observing. Think about this for a second. We're talking about technology that's not just theoretically possible, but that we're actively developing here on Earth. The Breakthrough Starshot project aims to send tiny spacecraft to nearby stars using exactly this principle. JAXA, the Japanese space agency, has already demonstrated solar sail propulsion with their Icaros mission. The physics is rock solid, but there's a big difference between our current capabilities and what would be required to explain 3i Atlas. We're talking about a sail potentially hundreds of meters across, made from materials that can survive millions of years in the harsh environment of interstellar space, attached to a craft that can somehow maintain its course and orientation across vast distances. The more Loeb thinks about it, the more the pieces fit. The elongated shape makes perfect sense for a light sail. You'd want maximum surface area to catch as much light as possible. The tumbling motion could be the result of a damaged stabilization system, or it might be intentional, allowing the craft to scan in all directions as it travels. Even the timing starts to make a strange kind of sense. These interstellar visitors aren't randomly distributed in time. We discovered Oumuamua in 2017, Borisov in 2019, and 3i Atlas just months later. What if they're not isolated objects, but part of a larger pattern? What if our solar system is actually crossed by these visitors regularly, and we're only now advanced enough to detect them? As word of the discovery spreads beyond the astronomical community, the reaction is swift and polarized. Some scientists urge caution, arguing that extraordinary claims require extraordinary evidence and that natural explanations haven't been fully exhausted. Others begin to seriously consider the possibility that we're witnessing something unprecedented in human history. The media, of course, goes wild. Headlines scream about alien visitors and interstellar spacecraft. But here's what makes this different from typical UFO hysteria. These aren't grainy photographs or questionable eyewitness accounts. This is hard data from the world's most sophisticated observatories, analyzed by teams of respected scientists using rigorous mathematical models. The public reaction is fascinating to watch. Some people are thrilled by the possibility that we might not be alone in the universe. Others are unsettled by the implications. If these really are alien probes, why haven't they made contact? Why do they seem so indifferent to our existence? But perhaps the most interesting response comes from the scientific community itself. Researchers who have spent their careers studying the orderly, predictable universe described by physics, textbooks suddenly find themselves contemplating possibilities that would have been dismissed as pure fantasy just a few years earlier. Dr. Alan Fitzsimmons from Queen's University, Belfast, leads one of the teams studying 3i Atlas. He's naturally skeptical of exotic explanations, preferring to exhaust all natural possibilities first. But even he admits that the observations are challenging everything they thought they knew about interstellar objects. The problem is time. Every day that passes, 3 Atlas gets a little bit fainter, a little bit harder to observe. The window of opportunity is closing fast. Soon, it will be too dim for even our most powerful telescopes to detect, and it will disappear into the darkness between stars, carrying its secrets with it. This creates an urgent atmosphere in observatories around the world. Every clear night is precious, every observation potentially crucial. Teams work around the clock, sharing data, coordinating observations, trying to squeeze every bit of information from this mysterious visitor before it's gone forever. As the data accumulates, one thing becomes clear. Whatever 3i Atlas is, it's going to change how we think about our place in the universe. If it's natural, it represents a new class of objects we've never seen before, with properties that challenge our understanding of planetary science. If it's artificial, well, that changes everything. The stage is set for one of the most important scientific debates of the 21st century. In laboratories and conference rooms around the world, brilliant minds are grappling with observations that seem to defy explanation. The universe, which seemed so well understood just a few years ago, has suddenly become mysterious again. And through it all, 3i Atlas continues its journey, speeding away from the sun at 67,000 miles per hour, oblivious to the chaos it's caused in the scientific community. Whatever it is, wherever it came from, it's given us a glimpse of something extraordinary and left us with more questions than answers. But to understand just how extraordinary these observations really are, we need to dive deeper into the physics. We need to understand exactly why the acceleration of 3i Atlas is so impossible to explain through natural means, and why some of the world's most respected scientists are seriously considering the possibility that we're looking at technology from another world. Okay, let's talk about why the acceleration of 3i Atlas is so mind-bending that it's making some of the world's smartest scientists seriously consider possibilities they never thought they'd have to contemplate. First, let me give you a sense of scale here. When 3i Atlas is accelerating at 0.003 meters per second squared, that might sound absolutely tiny to you. And you're right, if you were in a car experiencing that acceleration, you'd barely feel it. It's like the gentlest possible pressure on the gas pedal. But here's the thing, we're not talking about a car. We're talking about an object that potentially weighs millions of tons, hurtling through the vacuum of space. To accelerate something that massive by even that tiny amount requires enormous forces. Think of trying to push a freight train with your bare hands, except the freight train is the size of a skyscraper, and you're trying to push it from hundreds of millions of miles away. Now, in our solar system, there are really only a few things that can make objects accelerate. Gravity is the big one. The sun's massive gravitational field pulls everything toward it, and the complex dance of gravitational forces between planets creates the elegant orbital mechanics we see throughout the solar system. But gravity alone can't explain what we're seeing with 3i Atlas. The other natural mechanism that can accelerate objects in space is outgassing from comets. When a comet gets close to the sun, the frozen materials on its surface, water ice, carbon dioxide ice, methane ice, start to sublimate directly from solid to gas. This creates jets of material shooting off the comet's surface. And by Newton's third law, for every action there's an equal and opposite reaction. These jets push the comet around like tiny rocket engines. This isn't theoretical. We've observed it thousands of times with known comets. We can predict exactly how much acceleration a comet should experience based on its size, distance from the sun, and composition. The math works beautifully, and it explains the slight deviations we see in comet orbits all the time. But 3i Atlas breaks this elegant system completely. Dr. David Farnokia from NASA's Jet Propulsion Laboratory leads the effort to model 3i Atlas's trajectory. His team uses the same sophisticated software that tracks every known object in the solar system, from massive planets down to tiny space debris. This software has been tested and refined over decades. It can predict the position of spacecraft with incredible accuracy, guide missions to distant planets, and calculate asteroid impact probabilities. When they feed 3i Atlas's observations into this system, the results are baffling. The object is definitely accelerating, but there's no visible explanation for why. Spectroscopic analysis reveals none of the telltale signatures of outgassing that should accompany this level of non-gravitational acceleration. No hydrogen emission lines from water vapor. No carbon signatures from sublimating CO2. Nothing that would indicate the standard comet activity. It's like watching a car accelerate down a highway while the fuel gauge stays on empty and there's no exhaust coming from the tailpipe. The effect is undeniable, but the cause seems impossible. Let me put this in perspective for you. In the entire history of astronomy, we've catalogued and tracked hundreds of thousands of objects in our solar system. Asteroids, comets, planets, moons, spacecraft, everything follows predictable patterns based on well-understood physics. Occasionally, we see small deviations that we can't immediately explain, but they always turn out to have natural causes once we dig deeper. Atlas is different. The more data we gather, the stranger it becomes. The acceleration isn't just present, it's sustained and consistent. Most comet outgassing is irregular and unpredictable, creating jerky, uneven accelerations as different parts of the surface heat up and cool down. But 3i Atlas shows smooth, steady acceleration that looks almost deliberate. Dr. Darryl Seligman from the University of Chicago takes a different approach. Instead of trying to explain the acceleration through conventional outgassing, he explores more exotic possibilities. Maybe 3i Atlas is made of materials we've never seen before. Maybe it's composed of hydrogen ice, which would sublimate without producing detectable spectroscopic signatures. Maybe it's covered in some kind of dark organic coating that absorbs sunlight and drives out gassing of materials underneath. Seligman runs computer models exploring every plausible natural explanation. He considers objects made of pure hydrogen, nitrogen ice, carbon monoxide, anything that might sublimate near the sun without producing obvious visual signatures. He models different shapes, different compositions, different thermal properties. Some of his models come tantalizingly close to explaining the observations. A hydrogen iceberg, for instance, could potentially produce the observed acceleration while remaining nearly invisible to our instruments. But even the most optimistic scenarios require conditions that are extremely unlikely. We're talking about objects with properties unlike anything else we've ever seen in space, formed through processes that would be extraordinarily rare. And then there's the shape issue. Remember, light curve analysis suggests that 3i Atlas is highly elongated, possibly 10 times longer than it is wide. In our solar system, objects this elongated are unusual because gravity tends to pull everything into roughly spherical shapes. You need special circumstances to create and maintain such extreme proportions. Here's where things get really interesting. Dr. Loeb at Harvard starts approaching the problem from a completely different angle. Instead of asking, how can we explain this through natural processes? He asks, what would it look like if this were artificial? The answer is surprisingly straightforward. A light sail. Light sails aren't science fiction. They're real technology that works on a simple principle. Photons from the sun carry momentum, and when they hit a reflective surface, they impart a tiny push. For most objects, this radiation pressure is negligible compared to gravity and other forces. But if you have a very large, very thin reflective sheet, that tiny push can add up to significant acceleration. We've already demonstrated this technology in space. The Japanese Icaros mission successfully used a solar sail to propel a spacecraft to Venus. The Planetary Society's light sail missions have shown that small spacecraft can achieve measurable acceleration using nothing but sunlight. NASA is developing advanced solar sails for future deep space missions, but there's a crucial difference between our current solar sail technology, and what would be required to explain 3i Atlas. We're talking about a sail that would need to be hundreds of meters across, made from materials thinner than human hair, and capable of surviving millions of years in the harsh environment of interstellar space. Let me give you a sense of the engineering challenge here. The solar sails we build today are made from polyamide films, about 25 micrometers thick. That's about a quarter the thickness of a human hair. They're incredibly delicate and can only operate for a few years before radiation and micrometeorite impacts degrade them beyond usefulness. To explain 3i Atlas, you'd need a sail maybe 1 micrometer thick, 25 times thinner than our best current technology, and it would need to maintain its integrity for geological timescales. We're talking about materials science so advanced that we can barely imagine it. But here's the thing. The physics works perfectly. Loeb's calculations show that a light sail with the right dimensions and properties could produce exactly the acceleration observed in 3i Atlas. The elongated shape makes sense. You'd want maximum surface area to catch as much light as possible. The tumbling motion could be the result of a damaged attitude control system, or it might be intentional, allowing the craft to scan in all directions as it travels. Even more intriguingly, the acceleration profile matches what you'd expect from a light sail. As the object moves away from the sun, the radiation pressure decreases with the square of the distance, and so does the acceleration. That's exactly what we observe with 3i Atlas. Dr. Matthew Knight from the University of Maryland takes yet another approach. He specializes in studying the smallest particles in comets and asteroids, and he wonders whether 3i Atlas might represent something we've simply never encountered before, a class of objects so different from anything in our solar system that our usual models don't. Knight's team investigates whether the object might be a dark comet, something with comet-like composition, but no visible tail due to unusual surface properties or composition. Maybe it's covered in a layer of material that absorbs rather than reflects light, making outgassing difficult to detect. Maybe the sublimating materials are so exotic that our instruments can't identify them. But even these exotic explanations struggle to account for all the observations. The acceleration is simply too strong and too consistent to explain through any known natural process. As the debate intensifies, something fascinating happens in the scientific community. Researchers who have spent their entire careers studying conventional solar system objects find themselves grappling with possibilities that would have seemed absurd just a few years earlier. The conversation isn't happening in the shadows or on fringe websites. It's taking place in the most prestigious scientific journals, at major conferences, in the laboratories of leading universities. Serious scientists with impeccable credentials are publishing papers that seriously consider the possibility that we might be observing alien technology. Dr. Abraham Loeb publishes a paper in the Astrophysical Journal, letters laying out the mathematical case for 3i Atlas being an artificial light sail. The paper goes through peer review, the rigorous process where other experts evaluate the work for accuracy and methodology. It passes, which means the scientific establishment considers the possibility worthy of serious consideration. This is unprecedented. Never before have mainstream scientists seriously proposed that we might be observing alien technology in our solar system. The fact that such papers can now be published and taken seriously represents a fundamental shift in how we approach these mysteries. But the skeptics aren't going quietly. Dr. Alan Fitzsimmons argues that we shouldn't jump to extraordinary conclusions when natural explanations might still be possible. He points out that our understanding of interstellar objects is based on a sample size of just 3, hardly enough to establish what's normal for these mysterious visitors. Fitzsimmons suggests that 3i Atlas might represent a new class of natural objects with properties we've never seen before. Maybe interstellar space produces objects with characteristics unlike anything that forms in our solar system. Maybe the conditions between stars create materials and structures that we haven't imagined. The debate becomes more than just scientific. It becomes philosophical. Are we being too quick to invoke alien explanations for phenomena we don't understand? Or are we being too conservative, clinging to familiar explanations when the evidence clearly points to something unprecedented? As 3i Atlas continues its journey away from the sun, growing fainter with each passing day, the urgency intensifies. Soon it will be too dim for even our most powerful telescopes to track. The opportunity to gather more data is slipping away, and with it perhaps our best chance to definitively answer the question of whether we're looking at a natural object or something far more extraordinary. The physics of 3i Atlas has broken our models and challenged our assumptions. Whether the ultimate explanation turns out to be exotic natural phenomena or artificial technology, one thing is clear: this mysterious visitor has forced us to confront the limits of our understanding and consider possibilities we never thought we'd have to face. But if 3i Atlas really is artificial, if we're actually observing technology from another civilization, then the implications go far beyond physics and astronomy. We're talking about a discovery that would fundamentally change our understanding of our place in the universe and force us to grapple with questions we've only imagined in science fiction. So let's explore that possibility. Let's seriously consider what it would mean if 3i Atlas isn't a strange natural object, but something far more extraordinary, a spacecraft from another world, carrying out a mission we can barely comprehend. Let me ask you to imagine something that might sound like science fiction, but is grounded in real physics and engineering principles. Picture a civilization that achieved spaceflight maybe 1,000,000 years ago. Not the crude chemical rockets we use today, but something far more elegant and sustainable. They've mastered materials science to a degree we can barely comprehend, and they've decided to explore the galaxy. But here's the thing about interstellar travel: it's really, really hard. Even our nearest stellar neighbors are trillions of miles away. Chemical rockets would take tens of thousands of years to reach them. And that's assuming you could carry enough fuel, which you can't. Fusion rockets might get you there in hundreds of years, but the engineering challenges are enormous. What's an advanced civilization to do? The answer might be surprisingly elegant: send scouts instead of colonists. Build small, incredibly durable probes equipped with gossamer-thin light sails, and send them out by the thousands or millions. Each one follows a different trajectory, visiting different star systems, gathering data about planets, asteroids, the possibility of life. They're not meant to return. They're one-way messengers, designed to explore and report back across the vast distances of space. This isn't pure speculation. We're already planning exactly this kind of mission. The Breakthrough Starshot project, backed by physicist Stephen Hawking and tech billionaire Yuri Milner, aims to send tiny spacecraft to Proxima Centauri using light sails accelerated by powerful lasers. The plan is to get these postage stamp-sized probes up to 20% of the speed of light, reaching our nearest stellar neighbor in about 20 years. Now scale that up. Instead of our primitive technology, imagine a civilization that's had millions of years to perfect interstellar exploration. Their probes wouldn't be tiny postage stamps. They'd be sophisticated craft, possibly hundreds of meters across, equipped with sensors we can't even imagine, built from materials that can survive the harsh environment of interstellar space for geological timescales. Dr. Avi Loeb has run the numbers on exactly this scenario, and they're surprisingly plausible. A light sail just 1 micrometer thick, about 50 times thinner than a human hair, could produce the acceleration we observe in 3i Atlas. The sail would need to be roughly 300 meters across to generate enough force. But that's well within the realm of engineering possibility for an advanced civilization. Think about the shape for a moment. We've established that 3i Atlas appears elongated, possibly 10 times longer than it is wide. That's exactly what you'd expect from a light sail. You want maximum surface area to catch as much radiation as possible. A long, flat configuration would be optimal for both propulsion and sensor coverage. The tumbling motion makes sense too. If this is a damaged probe that's been traveling for millions of years, its attitude control system might have failed long ago. Or maybe the tumbling is intentional, a way to scan the entire sky as the craft travels, gathering data from all directions. Either way, it fits the profile of what we might expect from ancient alien technology. But let's dig deeper into what such a mission might actually look like. Imagine you're the mission planner for this hypothetical civilization. You want to explore the galaxy systematically, gathering information about as many star systems as possible. How do you do it? First, you'd want your probes to be incredibly robust. We're talking about a journey that might last millions of years, through the harsh radiation environment of interstellar space, dodging cosmic rays and micrometeorites. Your materials science would need to be absolutely extraordinary. Recent advances in our own technology give us hints about what might be possible. Graphene, sheets of carbon just one atom thick, is stronger than steel and more conductive than copper. Metamaterials can bend electromagnetic radiation around themselves, making objects effectively invisible to certain wavelengths. Self-healing polymers can automatically repair damage. Scale these technologies up by 1,000,000 years of development, and you start to see possibilities we can barely imagine. The propulsion system would be elegance itself. No fuel tanks, no complex engines, no moving parts to break down. Just a gossamer-thin sail, catching photons from stars, using the universe's own energy to navigate between worlds. As the probe approaches each star system, it could adjust its trajectory with minute changes to the sail's configuration, perhaps through programmable smart materials that respond to different wavelengths of light. Navigation would rely on the most stable references in the galaxy, pulsars. These rotating neutron stars emit regular pulses of radio waves with clockwork precision, some keeping time better than our most accurate atomic clocks. By triangulating signals from multiple pulsars, a probe could determine its position anywhere in the galaxy with extraordinary accuracy. It's like having a cosmic GPS system that works across interstellar distances. Power would come from multiple sources. Temperature differences between the sun-facing and space-facing sides of the sail could drive thermoelectric generators. Radioactive decay of long-lived isotopes could provide steady power for millions of years. The probe might even harvest energy directly from cosmic rays or the solar wind. But here's what really gets me thinking. If such probes exist, they wouldn't be traveling alone. A civilization advanced enough to build one would likely build thousands, maybe millions. They'd launch them in waves, each generation more sophisticated than the last, spreading across the galaxy like seeds on the wind. Most of these probes would pass through empty interstellar space, reporting back data about the void between stars. But occasionally, one would encounter a star system. It would adjust its trajectory, using its light sail to maneuver closer to the central star. Its instruments scanning planets and asteroids for signs of life, unusual chemistry, or other phenomena of interest. The probe wouldn't need to stay long. A few months or years would be enough to gather comprehensive data about the system. Then it would adjust course again and continue on its endless journey, perhaps toward a predetermined rendezvous point where multiple probes would meet to share data, or perhaps simply transmitting its findings back to its creators across the vast distances of space. If 3i Atlas is such a probe, consider what that means about its mission timeline. Based on its trajectory, it likely arrived from the direction of the constellation Lynx, possibly from star systems tens or hundreds of light-years away. At interstellar speeds, that represents a journey of hundreds of thousands or millions of years. Think about that timeline for a moment. This probe could have been launched when our ancestors were still learning to control fire. It's been traveling through the darkness between stars longer than our entire species has existed. And now, just as we develop technology sophisticated enough to detect it, it happens to pass through our solar system. Is that coincidence? Or are there thousands of such probes crisscrossing the galaxy, and we're finally advanced enough to notice them? Maybe our solar system has been visited by these silent messengers throughout history. But we never had the technology to spot them until now. Dr. Loeb suggests that these interstellar visitors might be part of what he calls a galactic internet, network of probes sharing information across vast distances. Each probe carries data not just about the systems it has personally visited, but about every system visited by every probe it has encountered. Over millions of years, such a network could map the entire galaxy in extraordinary detail. The implications are staggering. If this is true, then somewhere in the galaxy is a database containing detailed information about every star system, every planet, every moon that harbors life or shows potential for development. Our solar system would be just one entry in a vast catalogue of worlds. But here's what's both fascinating and unsettling about this scenario. The probe shows no interest in us whatsoever. It doesn't slow down to take a closer look at Earth. It doesn't attempt communication. It doesn't even adjust its trajectory to get a better view of our planet. It simply passes through our solar system like a tourist driving through a small town on the highway, noting our existence but not stopping to chat. What does that tell us about our significance in the galactic community? Are we simply not interesting enough to warrant attention? Are we too primitive to be worth studying in detail? Or maybe we're just one of millions of similar worlds the probe has catalogued over its long journey. Nothing particularly special or noteworthy. There's another possibility that's even more sobering. Maybe the civilization that built this probe is extinct. Maybe we're looking at the ghost of a dead species, their final automated emissary still carrying out its programmed mission millions of years after the last member of their race drew breath. This scenario has historical precedent on Earth. Ancient civilizations have left behind artifacts that continued to function long after their creators disappeared. Roman aqueducts carried water for centuries after the fall of the empire. Polynesian navigation techniques passed down through oral tradition outlasted the cultures that created them. Scale that up to a galactic civilization, and you might have automated systems that continue operating for millions of years after their creators are gone. The probe doesn't need to understand its mission or make conscious decisions. It just follows its programming, visiting star system after star system, gathering data that will never be read by the beings who sent it on its journey either way, whether its creators are still alive somewhere among the stars or turned to dust eons ago. The existence of such a probe would represent the most profound discovery in human history. It would mean we are not alone in the universe, that intelligence and technology are not unique to Earth, that other minds have pondered the same questions we're asking and developed capabilities that dwarf our own. But it would also mean we're not special. We're not the center of creation, not the unique flowering of consciousness in an otherwise dead universe. We're just another entry in a vast catalogue, another data point in someone else's grand survey of the galaxy. The psychological impact of such a discovery would be enormous. Religions would grapple with the implications of non-human intelligence. Philosophers would debate what it means to be human in a universe where we're clearly not the most advanced species. Scientists would scramble to understand technologies that might be millions of years ahead of our own. And perhaps most challenging of all, we'd have to confront the silence. Why don't they talk to us? Why don't they share their knowledge or offer to help us solve the problems that plague our world? Are we beneath their notice? Or are there rules we don't understand about contact between civilizations? The light sail hypothesis for 3I Atlas forces us to grapple with these profound questions. Whether or not it's ultimately correct, the mere fact that serious scientists are considering it represents a watershed moment in human thinking about our place in the cosmos. We're no longer asking whether life exists elsewhere in the universe. We're asking whether it might already be visiting us, cataloging us, studying us with the same detached scientific interest we show when we tag migrating birds or track whale populations. The engineering details of such a probe become more fascinating the more you think about them. How do you build something that can survive millions of years in space? How do you create materials that won't degrade under constant bombardment by cosmic rays? How do you design systems that can operate without maintenance across geological timescales? Consider just the problem of navigation. GPS satellites in Earth orbit need regular updates to maintain accuracy. But a probe traveling between stars would need to navigate autonomously for millions of years without any ground control. It would need to predict stellar motions, account for gravitational perturbations, adjust for the gradual drift of its reference pulsars. The computer systems would need to be unlike anything we can currently imagine. Not silicon chips that degrade under radiation, but perhaps quantum computers that use the structure of matter itself for storage and processing. Or biological computers that can repair themselves, grown rather than manufactured. The probe might carry the digital DNA of its creators, preserving their knowledge and culture long after their physical forms have vanished. But here's what really captures my imagination. If this probe is artificial, it represents a completely different philosophy of exploration than anything we've developed. Our space missions are expensive, limited, focused on specific objectives. We send one spacecraft to Mars, another to Jupiter, each one custom-built for its particular mission. This hypothetical galactic civilization takes the opposite approach. They build thousands of identical probes and scatter them across the galaxy like seeds. Most will find nothing interesting. Many will be destroyed by collisions or system failures. But enough will survive to gradually map every star system, every planet, every moon that might harbor life or resources. It's exploration through redundancy rather than precision. Quantity over quality, and over millions of years, it would be incredibly effective. You could survey the entire galaxy with nothing more than patient persistence and really good engineering. The more I think about it, the more I'm convinced that if we ever develop true interstellar capabilities, this is exactly how we'll do it. Not with massive starships carrying thousands of colonists, but with small, smart probes that can reproduce themselves using local materials, spreading through the galaxy like a technological virus. In fact, we're already taking the first baby steps toward this kind of exploration. Our Voyager probes are primitive versions of exactly this concept. Small, durable spacecraft designed to operate for decades in interstellar space. They carry messages for any alien civilizations that might find them. Just as these hypothetical galactic probes might carry information about their creators. If 3i Atlas really is such a probe, then we've just witnessed something extraordinary. The casual exploration of our solar system by a civilization so advanced that we register as barely more than an interesting curiosity. We're being studied the way we study bacteria. Noted, catalogued, and largely ignored, but perhaps that's not entirely bad news. At least, it suggests we're not threatening enough to warrant intervention. We're not disrupting their plans or posing any danger to their interests. We're just another young species taking its first tentative steps toward understanding the universe, worthy of a brief notation in their vast database, but not requiring any immediate action. The question is, what happens next? If these probes are part of an ongoing galactic survey, will more of them pass through our solar system? Are we now on their radar as a system with developing intelligence? And most intriguingly of all, as we become more technologically sophisticated, will we eventually rate a closer look? If 3i Atlas really represents alien technology, we need to confront a profound and unsettling truth. This isn't the first contact that science fiction has trained us to expect. There are no giant ships hovering over major cities, no attempts at communication, No dramatic encounters that change the course of human history overnight. Instead, it's more like finding an empty bottle washed up on a beach. You know someone else has been sailing these waters, but they're long gone, and all you're left with is evidence of their passage and 1,000 unanswered questions. Think about what this means for a moment. For decades, we've operated under the assumption that if we ever encountered alien technology, it would be designed to communicate with us. SETI, the search for extraterrestrial intelligence, has spent 50 years listening for radio signals from space. We've sent messages of our own, the golden records on the Voyager spacecraft. Radio transmissions beamed toward nearby star systems. The underlying assumption has always been that any civilization advanced enough for interstellar travel would want to make contact with other intelligent species. We imagine cosmic communities, galactic federations, wise alien mentors, waiting to welcome us into the broader family of intelligent life. But 3i Atlas suggests a very different reality. If it's artificial, it represents a kind of contact without communication, a brush with alien intelligence that's profoundly indifferent to our existence. We're being observed, catalogued, and ignored. This is actually not that surprising when you think about it from a different perspective. Consider how we study life on Earth. When marine biologists tag sharks or track whale migrations, they're not trying to communicate with these species. They're gathering data for their own purposes. The sharks don't know they're being studied, and even if they did, the scientists wouldn't necessarily try to establish a dialogue. Maybe that's our position in the galactic hierarchy. Maybe we're the equivalent of dolphins, interesting enough to study, intelligent enough to recognize as more than just animals, but not advanced enough to be worth talking to. The probe notes our existence, records our basic characteristics, and moves on. Dr. Loeb has written extensively about what he calls the zoo hypothesis, the idea that advanced alien civilizations might be aware of us but have chosen not to interfere with our development. Like wildlife researchers who observe animals without intervening, these aliens might have ethical guidelines that prevent direct contact with emerging civilizations. But there's another possibility that's even more sobering. Maybe the civilization that built 3i Atlas tried to communicate with emerging species in the past and found it counterproductive. Maybe contact with vastly superior technology is inherently disruptive to natural development. Maybe they've learned it's better to observe quietly from a distance. Consider what would happen if aliens landed on Earth tomorrow and offered to share their technology. Would it accelerate our development, or would it stunt our growth by making our own innovations seem pointless? Would we become dependent on their knowledge instead of developing our own understanding? There's a good argument that the kindest thing advanced aliens could do for us is to leave us alone until we're ready for genuine peer-to-peer contact. But the most unsettling possibility is the simplest one. Maybe they just don't care. Maybe intelligence is so common in the galaxy that discovering another species is no more exciting to them than discovering another type of bacteria would be to us. We note it, catalogue it, and move on to more interesting research. This scenario challenges our fundamental assumptions about our own significance. We tend to think of human intelligence as special, unique, the pinnacle of evolutionary achievement on Earth. But what if intelligence is actually quite common in the universe? What if the galaxy is teeming with civilizations at various stages of development, and we're just not that remarkable? The psychological impact of such a discovery would be enormous. Throughout human history, we've gradually had to adjust our understanding of our place in the universe. First, we learned that Earth isn't the center of the solar system. Then we discovered that our solar system isn't the center of the galaxy. Then we realized that our galaxy isn't the center of the universe. Each of these discoveries required us to become more humble, to accept that we're not as special as we thought. But the discovery of alien intelligence that considers us unworthy of contact would represent the ultimate humbling. We're not just not the center of the universe. We're not even interesting enough to talk to. The silence would be more profound than any message. It would tell us that yes, we are not alone in the universe, but no, that doesn't make us part of some grand cosmic community. We're just another entry in a vast database of catalogued worlds. No more significant than the millions of other species these probes have undoubtedly encountered. Religious communities would grapple with the implications. If humans are created in God's image, what does it mean that other intelligences exist and apparently consider us beneath notice? Some faiths would adapt by expanding their concept of divine creation to include the entire galaxy. Others might struggle with the challenge to human uniqueness that such a discovery would represent. Philosophers would debate what it means to be human in a universe where we're clearly not the most advanced species. Are human values and human achievements still meaningful if there are civilizations millions of years ahead of us? Does our art, our literature, our music matter if no one else in the galaxy cares about it? Scientists would face their own challenges. If alien technology is passing through our solar system, should we try to intercept it? Should we attempt to communicate with it even if it shows no interest in us? And how do we study something that's so far beyond our current understanding that we can barely recognize it as artificial? There would also be practical implications. If these probes are part of an ongoing survey, what information are they gathering about us? Are they noting our population levels, our technology, our impact on Earth's environment? Are we being evaluated according to criteria we don't even understand? Some people would find this prospect comforting. Maybe these advanced civilizations are keeping an eye on us, ready to intervene if we pose a threat to ourselves or others. But others would find it deeply disturbing. The idea that we're being watched and judged by superior intelligences touches on some of our deepest fears about surveillance and control. The political implications would be significant too. If we're truly being observed by advanced alien civilizations, it might encourage more international cooperation. After all, from their perspective, the differences between human nations and cultures are probably insignificant. We're all just members of the same primitive species, taking our first tentative steps toward understanding the universe. Or it might have the opposite effect. Some groups might see the existence of advanced aliens as validation for their own ideologies. Maybe these aliens are waiting for us to achieve certain milestones before making contact. Maybe they're testing us to see if we're worthy of joining the galactic community. The economic implications would be enormous too. If advanced alien technology exists, even if we can't access it directly, it proves that the challenges we face are solvable. Faster-than-light travel might be possible. Clean, unlimited energy might be achievable. The diseases and problems that plague humanity might have solutions we haven't imagined. This could drive massive investments in research and development as nations and corporations race to reverse engineer or independently develop technologies that we know are possible. Or it could have a demoralizing effect, making our own efforts seem futile in comparison to what's already been achieved by others. But perhaps the most profound impact would be on how we see ourselves as a species. The discovery of alien intelligence that considers us unworthy of contact would force us to grow up in ways we've never had to before. We could no longer see ourselves as the pinnacle of creation or the center of the universe. We'd have to accept that we're beginners, students in a cosmic classroom where more advanced civilizations have been learning for millions of years, longer than we have. This could be ultimately liberating. Instead of being burdened by the weight of cosmic significance, we could focus on our own development, our own growth, our own journey toward greater understanding. We could see challenges as opportunities to prove ourselves worthy of eventual contact, rather than as existential threats to our survival. The passage of 3i Atlas through our solar system, whether it's natural or artificial, represents a watershed moment in human consciousness. For the first time, we're seriously considering the possibility that we might be sharing the galaxy. with intelligences far more advanced than our own, and that they might not consider us significant enough to acknowledge. It's a humbling thought, but also an exciting one. If we're truly not alone, then the universe is far richer and more interesting than we ever imagined. And if we're currently too primitive to merit attention, that gives us something to work toward. Maybe someday, if we continue to grow and learn and develop, we'll become interesting enough to warrant a conversation. But first, we need to understand exactly what we're dealing with. If 3i Atlas really is alien technology, what can we learn from it? What does its design tell us about the engineering capabilities of its creators, and what might we need to achieve before we're considered worthy of more direct contact? Let's try to reverse engineer this cosmic visitor and see what we can learn about the minds that might have created it. If 3i Atlas really is artificial, every aspect of its design would tell us something profound about the civilization that built it, their priorities, their capabilities, their fundamental approach to technology. First, let's talk about materials. To survive millions of years in interstellar space, this probe would need to be built from substances that can withstand constant bombardment by cosmic rays, temperature swings from near absolute zero to hundreds of degrees, and impacts from microscopic particles traveling at enormous speeds. We're talking about materials science so advanced that our current technology looks primitive by comparison. Think about our most durable spacecraft. The Voyager probes, launched in 1977, are now showing their age after just 4 decades in space. Their power systems are failing, their instruments are degrading, and their communication abilities are weakening. They were built to last maybe 10 or 15 years, and the fact that they're still operational after 45 years is considered a remarkable achievement. Now scale that up to millions of years. What kind of materials could possibly maintain their integrity across such vast timescales? Recent advances in our own materials science give us tantalizing hints. Graphene, sheets of carbon just 1 atom thick, is stronger than steel yet incredibly lightweight. A single layer of graphene is nearly transparent, but stack enough layers together and you get a material that's virtually indestructible. For a light sail that needs maximum surface area with minimum mass, graphene or similar carbon structures would be ideal. But that's just the beginning. Advanced civilizations might have developed metamaterials, artificially structured materials with properties that don't exist in nature. These could bend electromagnetic radiation around themselves, making the probe nearly invisible to certain types of detection. They might incorporate self-healing polymers that can automatically repair damage from micrometeorite impacts or radiation exposure. Imagine materials that are alive in some sense. Not biological, but with built-in repair mechanisms that can rebuild damaged structures at the molecular level. The probe might carry templates for its own construction, able to fabricate replacement parts from raw materials it encounters during its journey. The propulsion system represents perhaps the most elegant aspect of the design. No fuel tanks that add dead weight. No complex engines with thousands of moving parts that can break down. Just a gossamer thin sail that catches photons from stars, using the universe's own energy for navigation and acceleration. But here's what's really clever about this approach. The sail doesn't just provide propulsion. It also serves as the probe's primary structural element. Everything else, sensors, computers, power systems, would be integrated into this thin, flexible sheet. It's like having a spacecraft that's all wing, no fuselage. The mathematics of light sail propulsion are well understood, but the engineering challenges are extraordinary. The sail would need to be perhaps 300 meters across, roughly the size of 3 football fields, yet thinner than anything we can currently manufacture. It would need to maintain its shape and orientation across millions of years without any active control systems. This suggests materials with programmable properties, substances that can change their configuration in response to different types of radiation or magnetic fields. The sail might literally reshape itself as it travels, adjusting its profile for optimal acceleration or communication with other probes. Navigation would rely on the most stable references in the galaxy, pulsars. These rotating neutron stars emit regular pulses of radio waves with clockwork precision. Some pulsars are so stable they rival our best atomic clocks. By triangulating signals from multiple pulsars, the probe could determine its position anywhere in the galaxy with extraordinary accuracy. But here's what's really sophisticated about pulsar navigation. It works across both space and time. Because we know exactly how pulsar frequencies change as they age, the probe could use pulsar timing to determine not just where it is, but when it is. This cosmic GPS system would work perfectly even after millions of years of travel. The computer systems would need to be unlike anything we can currently imagine. Silicon chips degrade under radiation within decades, but the probe would need processing power that remains stable across geological timescales. This might require quantum computers that use the structure of matter itself for storage and processing, or biological computers grown rather than manufactured. Consider the data storage requirements. Over millions of years, the probe might visit thousands of star systems, gathering terabytes of information about each one. It would need to store not just its own observations, but data received from other probes it encounters during its journey. We're talking about a distributed database that spans the entire galaxy. The probe might carry the digital DNA of its creators, compressed, archives containing their entire history, culture, and accumulated knowledge. Like a cosmic library, it would preserve the essence of a civilization long after their physical forms have vanished. Every probe would be a backup copy of everything they considered important, ensuring their legacy survives even if their homeworld is destroyed. Power generation would need to be equally sophisticated. Radioactive decay of long-lived isotopes could provide steady energy for millions of years. We already use radioisotope thermoelectric generators on our deep space missions, but an advanced civilization might tap more exotic energy sources. Temperature differences between the sun-facing and space-facing sides of the sail could drive thermoelectric generators. The probe might harvest energy directly from cosmic rays or the solar wind. It might even use the pressure of starlight itself to generate electricity, turning the propulsion system into a power source. But here's what really fascinates me about this design philosophy. Everything serves multiple purposes. The sail provides propulsion, structure, and power generation. The navigation system also serves as a cosmic clock. The data storage system preserves both mission information and cultural heritage. It's engineering with an elegance that our current technology can barely approach. This kind of multifunctional design makes sense for a civilization planning missions that last millions of years. Every component needs to be essential, reliable, and as simple as possible. There's no room for redundant systems or backup equipment. Everything has to work perfectly the first time and keep working forever. The probe might even be capable of reproduction. If it encounters a suitable asteroid or comet, it could potentially manufacture copies of itself using local materials. This would allow a small initial wave of probes to gradually populate the entire galaxy, each generation carrying forward the mission of the original creators. Think about the implications of self-replicating probes. You launch a few thousand from your home system, and within a few million years, there could be millions or billions of them scattered across the galaxy. Each one visits multiple star systems, gathers data, and occasionally builds copies of itself. It's exploration through exponential growth rather than linear expansion. This might explain why we're suddenly seeing multiple interstellar objects in such a short time period. If these probes can reproduce, then their numbers would grow exponentially over time. We might be reaching the point where the galaxy is so saturated with them that even our primitive detection systems can't miss them anymore. The communication systems would be equally sophisticated. Rather than trying to send signals back to a home system that might not even exist anymore, the probes would likely communicate with each other. They'd form a galactic internet, sharing information about every system they visit, every discovery they make. When two probes encounter each other, perhaps at predetermined rendezvous points near pulsars or other navigation landmarks, they download everything each other has learned. Over millions of years, this would create a distributed database containing detailed information about every star, system in the galaxy. The probe passing through our solar system might carry information, not just about the systems it has personally visited, but about thousands of others visited by probes it has encountered during its journey. In a few terabytes of storage, it could hold a complete catalogue of galactic civilization, which worlds harbor life, which have developed technology, which have achieved interstellar capability. From our perspective, the 3i Atlas represents technology so advanced it might as well be magic. But from the perspective of its creators, it might represent fairly conventional engineering, scaled up to galactic proportions. They've simply had millions of years to perfect designs that we're just beginning to imagine. The most humbling aspect of this scenario is how far ahead they would be in every conceivable way. Our most sophisticated spacecraft are crude chemical rockets that can barely escape Earth's gravity well. These probes casually cruise between star systems using nothing but starlight for propulsion. Our computers fail after decades. Theirs operate for millions of years. Our materials degrade under harsh conditions. Theirs rebuild themselves at the molecular level. Yet the basic principles aren't incomprehensible. We understand the physics of light sails, pulsar navigation, and quantum computing. We're developing metamaterials, self-healing polymers, and biological computers. The difference isn't in fundamental knowledge. It's in the sophistication of implementation and the timescales of operation. This suggests that while these hypothetical aliens are vastly more advanced than us, they're not using completely alien physics. They're using the same laws of nature we've discovered, but with an elegance and sophistication that comes from millions of years of refinement. If true, this gives us hope that we might eventually develop similar capabilities ourselves. We're not looking at incomprehensible magic. We're looking at extremely advanced engineering. And engineering problems, no matter how complex, have solutions. But it also suggests that if we want to join the galactic community represented by these probes, we have a lot of work to do. We need to develop materials that can survive for geological timescales, propulsion systems that don't depend on carrying fuel, and computer systems that can operate reliably for millions of years. Most importantly, we need to start thinking on different timescales. Our longest duration space missions are measured in decades. These probes are designed to operate for millions of years. That requires a completely different approach to engineering, a completely different way of thinking about reliability and longevity. As 3i Atlas disappears into the darkness between stars, it leaves us with a blueprint of what advanced spacefaring civilization might look like. Whether we're looking at actual alien technology or just an unusual natural object, the exercise of trying to reverse engineer it has shown us possibilities we never considered before, and perhaps that's the most important lesson of all. The universe is far stranger and more interesting than we imagined, and we've only just begun to explore it. Here's what gives me goosebumps. 3i Atlas won't be the last. In fact, it might not even be particularly unusual. We might be on the verge of discovering that these mysterious interstellar visitors are far more common than we ever imagined. And our solar system is actually a busy intersection on galactic highways we never knew existed. Think about the timing for a moment. For most of human history, we had no ability to detect objects like 3i Atlas. They could have been passing through our solar system regularly, dozens or hundreds of them, and we would never have known. It's only in the last few decades that we've developed telescopes sensitive enough to spot these faint, fast-moving objects, And even then, it took incredibly sophisticated automated survey systems to catch them. The human eye, even aided by telescopes, would never spot something as dim and fast-moving as Three-Eye Atlas. It required computer systems that could compare hundreds of images per night, flagging anything that moved between exposures. Now we're about to enter a completely new era of sky surveillance. The Vera Rubin Observatory in Chile, which began operations in 2024, represents a quantum leap in our ability to monitor the sky. This isn't just a bigger telescope, it's a fundamentally different approach to astronomy. Picture this, an 8.4-meter mirror, roughly the size of a basketball court, equipped with a 3.2 gigapixel camera. Every 3 nights, it will photograph the entire visible sky, creating a movie of the universe that captures everything that moves or changes brightness. Objects that are 10 times fainter than anything we can currently detect will show up clear as day in its images. When the Rubin Observatory is fully operational, astronomers expect to discover interstellar visitors not every few years, but every few months, maybe even more frequently than that. We might find that our solar system is actually quite busy. With these mysterious objects passing through on a regular basis, Dr. Avi Loeb predicts that within a decade, we'll have catalogued dozens of interstellar visitors. And here's what's exciting. We'll start to see patterns. Are they all similar in size and shape? Do they follow similar trajectories? Do some behave more strangely than others? If the artificial hypothesis is correct, we might start to distinguish between different types of probes. Maybe some are ancient artifacts, millions of years old, showing signs of damage and malfunction. Others might be newer, with more sophisticated capabilities and better preservation. We might even spot some that appear to be actively controlled, adjusting their trajectories in ways that suggest ongoing intelligence. But detecting these objects is just the first step. The really exciting part is what comes next, actually catching one. Project Lyra, proposed by researchers at the European Space Agency, represents humanity's first serious attempt to intercept an interstellar visitor. The concept is elegantly simple but technically challenging. Use gravitational assists from Jupiter and the Sun to accelerate a spacecraft fast enough to catch up with an object that's already left our solar system. The math is mind-bending. These interstellar visitors are moving at speeds that make our fastest spacecraft look like they're standing still. Catching up with one requires the kind of precision trajectory planning that pushes our orbital mechanics capabilities to their absolute limits. But it's possible. Using a series of gravitational slingshots, first around Jupiter to gain speed, then around the Sun for an even bigger boost, a properly designed spacecraft could achieve the velocities needed to intercept an interstellar object within a decade of launch. The key is timing. You need to launch when the planets are aligned just right to provide maximum assistance. Imagine what such a mission could tell us. If the object is natural, we'd get our first close-up look at materials that formed in another star system. We could analyze its composition, study its structure, maybe even determine which stellar system it came from, based on isotopic ratios that are like cosmic fingerprints. If the object is artificial, well, that would change everything. We'd have our first opportunity to study alien technology up close. Even if the probe is ancient and no longer functional, it would represent the archaeological find of the millennium. Every component, every material, every design choice would tell us something about the civilization that created it. But here's what's really exciting. We wouldn't have to wait for these objects to pass close to Earth. The new generation of survey telescopes will spot them while they're still far out in the outer solar system, giving us months or even years to prepare intercept missions. Dr. Robert Verick, who discovered both Oumuamua and several interstellar comets, is working on improved detection algorithms that could spot these objects even earlier. The goal is to identify potential targets while they're still beyond Neptune's orbit, providing maximum time to plan and launch intercept missions. the European Space Agency is seriously considering a dedicated interstellar object interceptor as part of their long-term science program. The concept involves a spacecraft kept in a state of readiness, capable of launching on short notice whenever a particularly interesting target is detected. But catching these objects is just one approach. The other strategy is to be ready when they arrive. NASA's Deep Space Network, the collection of radio telescopes that communicates with spacecraft throughout the solar system, is being upgraded with new capabilities specifically designed to study interstellar visitors. When the next mysterious object appears, we'll be ready with instruments that can detect even the faintest radio emissions, analyze the polarization of light reflecting off its surface, and measure its temperature with unprecedented precision. Every wavelength of electromagnetic radiation will be scrutinized for clues about the object's nature and origin. The James Webb Space Telescope, with its incredible infrared sensitivity, will play a crucial role in these investigations. Many materials that are invisible in visible light show distinct signatures in the infrared spectrum. If these objects are artificial, Webb might be able to detect the heat signatures of active components or identify synthetic materials that don't occur naturally. But perhaps the most important development is happening in computer science and artificial intelligence. The next generation of interstellar visitors will be studied not just by human astronomers, but by AI systems that can process vast amounts of data in real time, identifying patterns and anomalies that human researchers might miss. Machine learning algorithms are already being trained on simulated data, learning to distinguish between natural objects and potential artificial ones based on subtle patterns in their behavior and appearance. When the next mysterious visitor arrives, these AI systems will be able to analyze every pixel of every image, every data point from every instrument, looking for signs of intelligence or technology. Dr. Loeb has proposed something even more ambitious: active scanning of interstellar space using powerful radar systems. Instead of waiting for objects to get close enough to detect passively, we could actively probe the space around our solar system, bouncing radar signals off objects that are still too faint for optical detection. This approach has already been tested on a smaller scale. Planetary radar systems, like the one at Arecibo, have been used to study near-Earth asteroids in incredible detail, revealing their shapes, rotation rates, and surface properties. Scaling this technology up to detect interstellar objects would require enormous amounts of power and incredibly sensitive receivers. But it's technically feasible. The implications go beyond just finding more objects. If we can actively scan for interstellar visitors, we might be able to detect them months or years before they're visible to optical telescopes. This would give us unprecedented opportunity to study them throughout their entire passage through the solar system. But here's what really gets me excited about our growing capabilities. We're not just becoming better at detecting these objects. We're becoming better at understanding what they tell us about the galaxy as a whole. Every interstellar visitor carries information about conditions in other star systems. Its composition tells us about the chemistry of distant worlds. Its trajectory reveals the gravitational environment it has traveled through. Its age and condition provide clues about the hazards of interstellar space. Over time, as we catalog more and more of these objects, we'll start to build a picture of our galactic neighborhood that goes far beyond what we can see with traditional telescopes. We'll learn which star systems produce certain types of objects, how common different materials are throughout the galaxy, and what kinds of processes shape matter in the void between stars. If some of these objects turn out to be artificial, the information they carry would be even more valuable. Each probe would represent a data point in our understanding of galactic civilization. How common is intelligence in the universe? What kinds of technology do advanced species develop? How do they explore and communicate across the vast distances between stars? The next decade promises to be extraordinary for this field of research. New telescopes, better detection algorithms, improved analysis techniques, and potentially our first intercept missions will transform our understanding of these mysterious visitors from other star systems. But perhaps the most important development will be psychological. As we discover more and more interstellar objects, the idea that some of them might be artificial will become less shocking and more normal. We'll start to develop the mental frameworks necessary to deal with the possibility that we share the galaxy with other intelligences. Whether 3i Atlas is natural or artificial, it has already served an important purpose. It has forced us to confront possibilities we never seriously considered before. It has expanded our imagination and prepared us for discoveries that might once have seemed impossible. And make no mistake, more discoveries are coming. The universe is far stranger and more interesting than we imagined, and we're just beginning to explore it. Every mysterious object that passes through our solar system brings us one step closer to answering the most profound question we can ask. Are we alone? The answer might be more complex than we expected. We might not be alone, but we might not be significant enough to warrant contact. We might be sharing the galaxy with intelligences that are so far ahead of us that they barely notice our existence. Or we might be on the verge of the greatest discovery in human history. We might be about to learn that the universe is teeming with life and intelligence, and that our little solar system is just one stop on vast networks of exploration and communication that span the galaxy. Either way, everything changes. And it all started with a small, faint object tumbling through space, detected by automated systems on a Hawaiian volcano on a December night in 2019. Atlas has disappeared into the darkness between stars, but its legacy will endure. It has opened our eyes to possibilities we never imagined and prepared us for a future that might be far more interesting than we dared to hope. The cosmic ocean that once seemed empty now teems with messengers from distant shores. We're learning to read their signals, to understand their stories, and to prepare for the day when we might send messengers of our own. The age of interstellar archaeology has begun, and we're just getting started.